but I think it's not a good idea to make a project in that style that you want to really create something for blind people, but maybe it's a better idea to create something with some audio feedback and things like that and ask blind persons to test it. Ask them to be professional testers. And another approach could be that you start with really professional, really high-level interfaces. For example, there exist haptic interfaces. There are systems with which you can model three-dimensional objects, but just virtually. And you have, for example, this device, and you can move it, and you sometimes it has some resistance, and you can really feel the three-dimensional body. So another approach would be to start with such very interesting, very high-level devices, and then try to make something different, something similar, and reconstruct things like that. 1 minute, okay, that's my conclusion. Sensors alone do not inspire everyone. Nobody, only a few students did a project because they wanted to use a special sensor. They are not best inspiring. And the relevance of sensor technology should be made aware in several ways. In the school they use the term sparking. Each project has to start with sparking, and I think I need more sparking for these projects. I think the nice thing about sensors is that you can do really simple projects with simple programming concepts, and they are still relevant, they are still interesting because of the external sensors. And well, you can program games, but not just because it's funny. You can program games with some serious aspect. You can program a game and just as an illustration how one could use a sensor and sensor technology. So I want to conclude with this quote from this famous British neurologist: "We must humanize technology before it dehumanizes us." And that's it. Thank you very much for listening.
Thank you, ma'am. I'm just wondering, did you begin with an experiential component for your students at all? An example of going around and being blindfolded or something so they can experience what it means?
Sorry, going around. Yes. Okay, that's a good idea, yeah.
Oh, so you didn't begin that way. I was wondering if you perhaps began with an experiential learning moment where they're actually knowing what it means to be blind, to make the blind design relevant to them? Or what point did you begin to introduce the aspect of designing for blind people?
Okay, this was just an option to design something for blind people.
Okay.
It was not that everybody had to design something for blind people.
Okay.
The project goal was quite open.
Okay.
There are many reasons to think about interface technology, not because to do something for handicapped people. There are many other reasons too.
I agree that there are many reasons, but as someone who has friends with cerebral palsy, blindness, everything whose lives have been enhanced by design, it's something that I'm always happy to hear about and encourage wherever it can be encouraged. Do you want to comment?
Any other questions or comments?
Well, I think there are two things. First, I think that this sensor technology is really something important aspect of computer science. And the second thing is that it's really possible to do something relevant with very, very little code. And it makes the project much richer because you have to think about electricity, you have to think about the sensors themselves. and things like that. And okay, that's another 2 minutes. And thinking about using centric technology, sensor technology, and making it open for special groups in our society, I think this makes it more serious. Then the game is not that important, but the game is the part which makes fun, and the other thing is the part which makes it relevant.
Any other questions?
Am I too loud?
Hello, test.
I know I'm usually loud, but I mean in sound.
Okay, keep it us. Okay, so just a second. So I'm very sorry for this delay. Fortunately, it looks like we managed to solve it. Okay, so without really losing any time, Kronis Kynikos is the first presenter in this session. Kronis, over to you.
Okay, so hello everybody. Let me just share my screen and hope you can see it. Is that okay?
Oh, yeah.
Too loud.
Okay.
Stop shouting.
So
Kronis, maybe you should maybe just turn your volume a little bit down.
turn the volume down. Okay.
This
This better?
not really.
This better?
No.
No. I don't know what to do.
We
I'll try not to talk too loud. Is that okay? Is it better now?
Yes. Stop him
Okay,
doing it.
thanks.
Don't let him do anything.
So let's start. What I wanted to talk about was, as you know, in recent years, I've been concerned about the role and positioning of constructionist activity, constructionist designs, constructionist reforms within a much wider situation and context where there are conflicting agendas or parallel agendas for reform or for pedagogy or for technology at that. With this presentation, my interest was to see whether it is possible for all of these things to coexist without looking as if constructionist is either a silo pedagogy or a silo reform, isolated from others as a total solution, or conflict with everything else that's going on. So the context to discuss these ideas was an initiative I've been involved in for the last 4 or 5 years in collaboration with the Ministry of Education in Greece and their project, which is called the Digital School. I'll tell you a couple of things about it. So I was considering the history of constructionism from the days where it was just coined by Appert as meaning-making through programming figural models, because that was the only affordances available. And then we had the era of multimedia dynamic manipulation, where programming was perceived more like multimedia authoring than expression of meaning. And then we had the era of information communication technologies, where expression was totally out of the picture, and mainly connectivity and group work and collaborative learning was the name of the game, and the era of social media. And I'm considering that this age that we're living in is the age of scaling up, the age of management and administration and scale economy, and the age of large portals, which I call infrastructures, digital infrastructures, because in the sense that this is the way they are perceived and mediated. And the idea is we have, in a sense, some kind of refocusing on coding and making. But some people are saying that this is just a rebranding of constructionism, And maybe this is an opportunity to think whether this is so or how we can convey it to the wider community. A couple of things about the Greek Digital School project. It consists of several things, most importantly two very large portals. One portal is, they've taken the actual interactive curriculum books. We only have one curriculum book in one national curriculum in Greece. And they, the HTML versions of them, they assigned to teams of people to create links to places or to videos or to anything they thought was appropriate, and put those links in amongst the curriculum book text. And the Photodendro portals, this is another large portal where all those links are aggregated with carefully created metadata, not connected to the curriculum book. I was assigned the interactive books and the Photodendro portal for mathematics, and I worked with around 30, or a little more than 30 colleagues who were of diverse expertise, designers, secondary, primary developers. I mean, they were excellent at GeoGebra development or at Turtle Worlds development, teacher educators and science teachers. And all of them got together to create links for mathematics education. After lots of discussions, the idea was that we wanted to have a coherent intervention, coherent pedagogy through this digital school initiative. And we thought that the idea of a micro-experiment, not a micro-world, or an experiment, or some kind of an exemplary geometry problem that could be demonstrated by the teacher to students, but little focused exercises or experiments that allowed students to dynamically manipulate or to change some kind of model, mathematical model, and with this experience discuss the underlying mathematics. There were textual questions and directions within each of these experiments, and occasionally there was an open question at the end, allowing for some more investigative mathematical activity. These were designed by groups of colleagues, not by one colleague, each micro-experiment, and each group of colleagues had a heterogeneous expertise. There was always a pedagogy specialist with a technical specialist working together. So in a matter of around 3 years, there were 1,800 web-based micro-experiments developed from year 3 through to 11 for mathematics. Most of them with GeoGebra, because this was basically the only available web-based tool, authoring system for mathematics at the time, and a fair amount with TurtleSphere, which is like Turtle Worlds in 3 dimensions, a tool that we developed in my lab, which is also, again, web-based. You can play on any device. I'll show you in a minute. And within that era of around 4 to 5 recent last years, there were another 2 reforms happening at the ministry, and we didn't leave them as totally independent. One of them was a new curriculum for mathematics, where we discussed and integrated the sense that technology should be a means for expressing mathematical meanings. And the new curriculum was emphasized mathematical activity and the idea of mathematical literacy, and not mathematics as a discipline in itself, standalone abstract discipline to be demonstrated and explained to students. That was the gist of reform. And there's been a wide-scale longitudinal teacher education program for the last 10 years. Up until now, the result has been that we have 98 teacher educators who went through a 350-hour training-long course, and they have reached 2,500 out of the 7,000 teachers in the country. So it's kind of middle scale and progressing with respect to using digital media in their courses. So this is the context within which all of these things worked. What I wanted in particular to discuss now is whether these infrastructures can be designed so that they can be used not only in a way that's understood by a very large number of teachers without having any means of supporting or helping them, but also at the same time used by teachers and students who can engage in constructionist activity. So I asked a teacher friend of mine who was a student in the master's course, Dimitris, who is now doing a PhD, to then just pick a few micro-experiments and try changing, see if he can find any interesting reason to change them. Try changing them and then giving them to his students to see what happens. Let me show you a couple of things live, because this is not possible on paper, of course. I'm going into Explorer. This is Turtle Sphere. And this is a typical micro-experiment. I don't know if you can see the letters on it. And it says, Costas' team tried to write a procedure which would create a rectangle which is not a square. They wrote parallelogramo. Hang on. This is, just wanted to give you this one first. This is what was in the digital school portal, in the interactive books. Yannis's team tried to write a procedure to create a square. They wrote the square procedure you see below, but when they executed it, the resulting figure was not what they thought it would be. This is the resulting figure. And if you click on the trace, you have, I don't know if you can see this, you have the possibility to dynamically manipulate the value of the variable. And you can see that even when the figure closes, it's not a square. So the students are supposed to go back into the code and realize that the terms are not right and change the formalism in order to recreate the procedure and make it work. That's the idea of a micro-experiment. What Dimitris thought of doing was to change the exercise and change the code and give students a parallelogram. Say that, again, the same story, somebody tried to make one and couldn't manage it. Can you fix it? So to get the students to think of a little more complicated relationship that the adjacent angles are supplementary. And then Dimitris thought of asking the students to create a parallelogram which could never be a square. That was the exercise. And in amongst the students who had lots of ideas and worked in groups, there were some that thought of ways of doing this, and Dimitris would go in and show them that this was not the case, because he would move the sliders and show that at some point it did become a square. So we have two student idea solutions here. One of them, they decided to say forward x plus 12, forward x for the two subsequent segments, which means that they thought of inserting a function, inserting a functional relationship in amongst two variables in order to achieve what Dimitris has asked them to do. The other is equivalently another group of students that said 2 times x. And there was a lot of playing around and a lot of joking and a lot of realization that this could never become a square, and they were teasing their teacher and provoking him to make a square like this. So there was an interaction where the students themselves thought of and coined an algebraic relationship between two variables on a geometrical problem. This is one example. The other example is, this is what Dimitris found in the interactive book. It's a simulation with scales, and it's about equations, and the idea is that you're supposed to find x by isolating x on one side of the scale and seeing how many known weights you need for it to be balanced. And what Dimitris thought was that he wanted the representations to become different. They were too simplistic for him and his classroom. So he inserted more mathematical representations. Here you see you have figural representations of the amount of weights that you have in each container where you can't see the weights, blue balls and red balls. And the red balls weigh 20 grams each. But Dimitris asks the students, how can you work out, he asked them if there are any chances that the scales are faulty, and then whether they can work out each blue ball, how much each blue ball weighs. So you could see students having strategies like putting the same number of weights on both scales to see that they are faulty, and then to see how many weights, known weights they need to add, which is in this case 3 times 20, 60, to see what the fault is. And then their strategy for finding the blue scale was to augment one scale by one, and then see how many red scales they need to add. So here they need to add another 2, and to see how much the blue scales weigh, which is 40 grams each. The third example, so in this case, what Dimitri did to the micro-experiment was play around and change the representations, and to also draw attention rather from that to equality to attention to equivalence. That was his agenda. And in the third situation, we have a classical geometry problem. This is what Dimitris did to it. Originally in the text, we have the diameter, and AC is another diameter in the text. So, okay, yes, yes? Yes, sure. So this is how it was in the geometry, in the curriculum book. What Dimitris did was to change it and have one chord and one diameter, and ask students what happens to the intersection point. And what is important here, and I wanted to show you, is that one student, without being suggested or told or encouraged, decided to create this point, O dot, and see what happens, which is at the center of AC, and see what happens to segment O dot as the figure changes. So he had an intervention that constructed a segment and was looking at the segment to try out his investigation. Now, coming back to finish up, let me just, okay, here we are. There's 3 issues that raise in my mind from this experience with Dimitri. Of course, it's happening elsewhere as well, and I keep asking my teacher educators, and they tell me that there's a lot of teachers who have opinions and are changing some of the micro-experiments from the portal. Some of them are creating their own little portals, personal portals themselves, with ideas from the digital portal, and some of their own as well. So it's kind of spilling out of the infrastructure. So one perspective on this is to think of constructionism as existing amongst evolving grand agendas, and consider the role of constructionist mathematical activity within this kind of evolution. Try and find methodologies and approaches and the language, and also the activity and the pedagogy, which coexists within these large-scale initiatives, which are a phenomenon of our times because of globalization and because digital media allows this, and because we're going, of course, through the age of administration and reform. And the idea of whether it is possible to integrate these agendas, allow them not to coexist as conflicting agendas or unconnected agendas. but to address the essence and the characteristics of both of them, and to think about how constructionism can exist in amongst, for instance, reforms that focus on equity, on scale economy, on digital citizenship, and on diversity using technologies. Listen. Question about the game of what's in it, constructionism. Well, in this case, we thought that there was added value in this intervention with respect to helping students at wide scale think of mathematics as an experiential subject, something that they live and have experience with, and the idea of democratizing resource design of the teachers and students and remix it. So these were the two things that we perceived constructionism brought out of the visibility that was afforded. Visited the site in Greece. It has about 400 hits every month. So thanks.
Okay, good. Thank you. Can you hear me, Ronis?
Yes.
Okay, good. So, ask questions. Do we have any questions? Well, actually, Ronis, I'm not insisting on asking because we are a little bit late. So, thank you very much. I'm afraid we are going now to. Well, thank you, of course, again. And
thank you. That's fine. Thanks, everybody. Greetings.
And greetings to you. It's pity you cannot be here with us. And I'm sorry that we couldn't start exactly on the time. But
that's fine.
I'm sorry we have to disconnect now because we are going to send data for the second.
Okay.
Okay, so thank you very much. Bye-bye. Bye.
Thank you.
Hello? Maybe we should turn this volume on.
Thank you, John, and also another member of our project team is here, Dave, as well. So our project started about a year and a half ago, and it's a 3-year project, so we're around halfway through at the moment. So I'm going to be sharing with you some information about the design process that we've been following today, and sharing some very early findings as well from the work that we've done. So just to give you a little bit of background to the project, I thought I'd share a history of maths and programming in schools in England. So one of the key aims of the project is to develop children's mathematical abilities through learning to program. So we wanted to take into account what's being done before. So it first came to attention in the 70s and 80s that the potential of learning maths through tools such as BASIC and Lego programming. But by the 90s in England, this early enthusiasm that many teachers had diminished somewhat. And although the government made a real push for equipping all schools with computers, there was more of a focus on how we could use the computers. And the actual concept of programming was quite a minor part of the English curriculum. And by the early 2000s, the subject of ICT, or Information Communication Technology, was prevalent in schools, and many lessons were focused on using computer applications like Microsoft Word, that kind of thing. But this all changed in 2012 with the publication of a report by the Royal Society that was looking at the state of the ICT curriculum in England. And this report received a lot of attention across the country, a lot of coverage in the media. And a result of this report meant that the ICT curriculum was scrapped entirely, both at primary and secondary level. And in 2014, compulsory computing curriculum came in at primary school level, and there was also a new computing curriculum introduced at secondary level. So within our project, we're focusing on the 9 to 11 age group, which is the 2 years at the end of primary school. and it's currently mandatory for all schools to teach the new curriculum. And this curriculum broadly covers these three key points. So it specifies that people should learn about how to design and build programs, that they should be able to understand how the computing system works, and also be taught about elements of e-safety, and have the opportunity to use a range of different technologies for specific goals. So within this curriculum, programming is seen as a key aspect of it, but it's not the entire curriculum. So digital literacy is still seen as a core component as well. So just to give you an overview of kind of what's happening at the moment in terms of the introduction of this curriculum, from speaking to the teachers on our project, we've found that computing is typically being taught around an hour a week, but this can really range from anything from a very short lesson of 30 minutes up to 2 hours. And it's typically taught by the class teacher, who is a generalist, and many of them have no formal qualifications in this area, so they're learning everything newly and kind of as they go along. There is, however, a deluge of free resources and also schemes that you can buy in, and some schools are developing their own resources in-house. And these are some examples of some of the things that teachers in England have told us that they're using. So there's really a broad range of different tools and resources that schools are using, and with Scratch being quite a common one. So over half the teachers that we are working with at the moment have used Scratch before. So coming back to our project specifically, the aims of our project are to address this new computing curriculum using a specially set of design materials for use with Scratch. We also want to support problem solving and reasoning in mathematics through programming in Scratch. And the ultimate aim is to boost the end of Key Stage 2 maths score. So this maths test that all pupils in the country must take at the end of primary school will be looking at the results of these tests to see if there's been an improvement in the pupils that have undertaken that intervention. And it's quite a big project, so we're working with over 100 schools in the country, and they're spread across 6 regional hubs. So we've got schools in London, in the southwest, and also in the northwest of the country. And these 100 schools are being split into 2 groups. So we've got one group who's the treatment group, who began our intervention in September. And then we've also got the second group, the control group, who will start next September. So alongside an independent evaluation, so we're conducting a randomised control trial. So we have the treatment group and the control group, and we're comparing the outcomes of the children in the 2 different groups. Our team is also looking at undertaking a qualitative piece of research so we can get a sense of mechanism. So the randomised control trial is undertaken by independent evaluators at Sheffield Hallam University, and our focus is on qualitative